All right, I'm going to take you through these review questions and then post this video to YouTube, but if you're listening to this, then you already know that. So number 1 says, calculate the work done in each of the following situations. A force of 25 newtons pushes an object 5 meters across the floor. Calculate the work done. The formula of work equals force times distance, which is going to be 25 newtons times 5 meters. 5 times 25 is 125. That's 125 joules. So that's 125 joules. B says a mass of 5 kilograms is lifted 6 meters. 5 kilograms, 6 meters. When you're lifting up a mass, you have to lift with force of gravity. So that means work is going to be equal to the gravitational potential energy that you gain, which is mgh. So that means we're going to go 5 kilograms, 9.8 newtons per kilogram times 6 meters. You guys can finally answer that one because I can't do it in my head. Let's scroll down a little further to part C. It says a force is exerted on a car stuck in the snowbank. The car doesn't budge. The work done, if there is no distance, is 0 joules. D, a skater glides forward on the ice while exerting a force 50 newtons upwards. Well, the force is up. Distance is forward at 90 degrees to each other, and that means again there is no work. You have to have a force and distance that are in the same direction or oppositely directed to have any work done. Pushes a cart forward 25 newtons, the cart moves 10 meters, friction force is 5 newtons. Well, that's a tough one, because what work are we trying to figure out? The work Joel does is just going to be 25 newtons times 10 meters, which is 250 joules. But if we also wanted to know how much work friction does, we would go work equals negative 5 newtons, because the force of friction is backwards, times 10 meters, that equals negative 50 joules of work. So that's the work done by friction. The 250 is the work done by Joel. This question doesn't specify which work we want, and I would be more specific on a test question. F says a puck starting at rest is accelerated by 50 newtons of force. After 5 seconds, the puck is moving at 8 meters per second. Calculate the work. Well, work can also be the amount of energy gained by an object, and the type of energy being gained here is kinetic energy. So in this case, I'm going to say work equals kinetic energy, and that's 1/2 mv squared. Unfortunately, we don't have a mass here, so we're going to have to find an alternate method. So why don't we try finding out how far the thing goes, because we can also find work by going force times distance. We know the force, and we can calculate the distance over here. Let's go v1 equals 0, because it says the object starts at rest. Let's say that v2 equals 8 meters per second, and it does all this in 5 seconds. We can apply equation number 2 from linear kinematics. That's v1 plus v2 times t over 2. That's going to be 0 plus 8 times 5 divided by 2, which is going to be 20 meters. Now let's go back to our work equation. The work equals 50 newtons times 20 meters. 50 times 20 is going to be 1,000 joules of work. Number 2 says calculate the force needed to do this much work and moving that much distance. It's just rearranging the work equation. We'll draw that triangle. That's something we like to use. Work equals force times distance. And now we're going to solve for force. Force equals work over distance, which is 100 joules over 20 meters, which is going to be 5 Let's scroll down and do another one. Number 3. 50 joules of work is done by an applied force of 8 newtons. Find the distance the object moves. Same thing, except now we're solving for distance. Distance will equal work over force. 50 joules, 8 newtons. Again, that's not one that I can do in my head. That will give you the number of meters that the object moves. 50 divided by 8. 100 joules of work is done to move an object 20 meters. Find the force meter. We're just repeating ourselves now. Force equals 100 joules over 20 meters. I feel like I've done this one before. Equals 5 newtons. A block of mass 15 kilograms is at 3 meters. Find the gravitational potential. Yeah, we can do that. G equals mgh. 15 kilograms, 9.814 G, 3 meters. Put that to your calculator and you'll get the number of joules of gravitational potential energy that that particular block has. A ball, mass 5 kilograms, moving 4 meters per second, find EK. Here's our EK formula. EK equals 1/2 mv squared. That's going to be 1/2 5 kilograms, 4 meters per second. Square it, and that's going to give me 4 times 4 is 16, half of it is 8, 8 times 5 is 40 joules of kinetic energy. A 2 kilogram bird moving at 0.3 meters per second, height of 45 meters. Find EG and EK. Alright, let's start with EG equals mgh, that's 2 kilograms, 9.81, and a height of 45 meters. It's not one I can do in my head, but that'll give you the EG. The EK, as always, is 1/2 mv squared. And that's going to be 2 kilograms, actually 1/2 at the start. Times 2 kilograms times the speed squared, 0.3 meters per second. It's going to be squared. That will get you the amount of kinetic energy. Number 8 says a book held at 5 meters has an energy of 55 joules. Find the mass of the book. Hard to make a triangle for this one, but EG equals mgh. I'm just going to put all the numbers in and see how I can rearrange it. All right, so 55 joules equals, try to find the mass, 1 for G, and a height of 5 meters. So we're going to take the 55 and divide 9.81 and the 5. So it's going to be m equals 55 divided by 9.81, also divided by 5. Now we'll give you the mass. Give you the mass in kilograms. How much potential energy is needed to get a 4.5 kilogram object up to 12 meters? How much potential energy? That's EG. It's going to be gravitational potential. GH, 4.5 kilograms, 9.81 newtons per kilogram times 12 meters. That will get you the amount of potential energy to get up to 12 meters. Could have also said how much work it would take to get up to 12 meters. Do the same thing. 5,000 joules of energy is needed to raise a mass 6 meters. Calculate the mass. Once again, we're going to be going from the gravitational formula, EG equals mgh. And we'll be solving for mass again. So mass will be equal to EG over GH. We have all those values. 5,000 for the energy. 5,000 joules divided by 9.81. And the height is 6 meters. That'll get you your mass in kilograms. Now we've got a 2,500 joules of energy is needed to raise a 2.5 kilogram mass. Find the height at which it needs to be raised to. Same formula as before, except now we're solving for height. So it'll be EG divided by mg. So this time it's 2,500 joules divided by 2.5 kilograms to get 9.81 newtons per kilogram. That will get you the height in meters. 2.5 kilogram ball is moving 4.5 meters per second. Find the kinetic energy. Question like this today. So it's 1/2 mv squared because it says kinetic energy, and that's the formula for kinetic energy. So that's going to be 1/2 2.5 kilograms, 4.5 meters per second. Don't forget to square that 4.5. And that gives you joules of kinetic energy. 13 says a 5 kilogram ball is moving that fast, 2.5 meters per second, height is 6 meters. Find a bunch of stuff. Kinetic energy, 1/2 mv squared, so it's going to be 1/2 5 kilograms, 2.5 meters per second, and that'll be squared. The potential energy will be mgh, which is going to be 5 kilograms, 9.81 per g, 6 meters high. And the total energy is always just going to be on the screen. E total equals EK plus EG. And scrolling down to 14. A ball of mass 2 kilograms has that much energy. How high off the ground is it? We just did one like this a few questions back. If I rearrange the gravitational formula, EG over mg, it will be 44 joules over 2 kilograms times 1. Just make sure you get the order of operations right in your calculator. Some calculators may require that you bracket this before you or after you hit divide, I guess. What's the gravitational potential energy of a rock 25 kilograms when it's 50 meters off the ground? Well, that's even easier. Go backwards, mgh, 25 kilograms, 9.1, rate of 15. That will give you your gravitational potential energy. A lot of repetitive practice here, but it should get you in good shape for the test. What's the kinetic energy of a baseball? Now we're finding EK again. Well, that hopefully we have 35 meters per second, and that value is squared. That will be joules of kinetic energy. Don't forget to square the 35. 17 says a rock mass 2 kilograms falls off a cliff 50 meters high. What's the potential energy at the top of the cliff? All right, so now we're getting into a real conservation of energy question, I think. But anyway, at the top of the cliff, it'll have just EG, which is mgh, which is 2 kilograms, 0.81 newtons per kilogram, and it's 50 meters high. That will give you the EG at the top of the cliff. What's the total energy of the rock? Well, the total energy is constant throughout any of these questions, so the total energy will be equal to whatever the gravitational energy was from the previous question. That is the total energy. In part C, I'm actually going to need to calculate the gravitational potential energy at the top now, because I'm going to need that number in order to find the speed of the rock from the kinetic energy. So this gave me 981 joules of energy. So that makes the total energy 981 joules of energy. Now I'm going to scroll down and we're going to use that stuff to find the speed of the rock as it hits the ground. Now we can use that 981, but just because this will also help with other questions, I'm just going to write ET initial equals E total final. Initially, there's just gravitational energy. And at the end, it converts it all to kinetic energy. The EG we already calculated is 981 joules. And then over here, you're going to have 1/2 mv squared. More specifically, we're going to have 1/2. And what was the mass of that rock again? Let's go back up, and it is 2 kilograms. 1/2 times 2 kilograms times v squared. If we do some algebra and isolate for v, we're going to find that our answer is 31 meters per second. I'll circle that one for that. That'll represent one of the tougher questions you'll have to solve on the test. Energy transformation equations we didn't really cover, but basically you're just writing an arrow to show what type of energy you start with, EG, and arrow, what are you converting it into? EK. This is what you begin with, and this is what you end with. 18 says 4,500 joules of energy is used for 6 seconds. Find the power developed. That's a lesson we're going to do just before this review. Power is equal to work or energy over time. So I'm actually going to write both. Energy used, developed, transferred, whatever. So, in this case, that's 4,500 joules divided by 6 seconds. How powerful is that transformation? 4,500 divided by 6 is 750 joules per second, or watts, which is the symbol capital W. Number 19, also a power question. Find the power needed in order to raise a 3,000 gram object to a height of 6 meters in 1.2 seconds. So first I need to find the energy. The energy is to lift something up as mgh. So that's going to be 3,000 grams, which is 3 kilograms. 9.81, this is mgh, times 6 meters. That will give me the energy. So I'm typing in my calculator, 9.81 times 6 equals, I got 176.58, so I write that at 176.58 joules of energy. If I want to find the power, I just take that energy and divide it by time. So that's the 176.58, 176.58. And that's joules of energy divided by 1.2 seconds. Joules per second, or watts, is the units of the answer. 147 watts. Answer right there. The last question, I've almost run out of room. Let's see if I can extend the page here. There we go. 2 kilogram ball is pushed by a force of 20 newtons for 5 meters in 15 seconds. Find the power. All right, first find the work. Because remember, power also means work over time. Work's equal to force times distance. So why not go force distance over time? I might actually have all those values. I don't even need the mass then, do I? It's just going to be 20 newtons times 5 meters divided by 15 seconds. It equals, that will be the power. 20 by 5 divided by 15 equals 6.7 watts of power. It looks like that just about covers all the review questions. Just going back to look at my sheet. Yeah, there's just 20 of them. The only real tough one in there, the only conservation of energy question, is back at this number right here, number 17. So pay close attention to that one. I actually don't really want you guys to hand in your conservation of energy assignment today, because I have no chance of getting it back to you, and those will be the most challenging questions that you have. So that's it. Now I have to figure out how to post this to YouTube. That's me getting into my chair, taking a sip of my coffee, and signing up.